Jnanam paramam dheyam. Knowledge is supreme.
Now, let us move on to the external diffusion. We looked at the internal diffusion. What is the method to use the experimental observable data in order to find out whether the reaction is being conducted under internal diffusional limitations. So, next let us look at the external diffusional limitations. So, one has to use a criteria developed by Mears, it is called the Mears criterion. So, Mears's criterion can be used to find out whether the catalytic reaction is being conducted under external diffusional limitations, that is mass transport diffusional limitations. That is the transport of species from the bulk to the surface of the catalyst, is that limiting the reaction severely. So, the expression is, suppose if minus R A is the observed reaction rate, it is the observed rate, then the criterion is that if minus R A into rho B into R into N divided by K C into C A bulk, if that is smaller than 0.15. So, if the ratio of, if this expression on the left hand side, that is basically contains the observed reaction rate. So, the observed reaction rate multiplied by the corresponding density, bulk density of the catalyst. So, the bulk density of the catalyst rho B is given by 1 minus phi into rho C, where phi is the porosity of the bed that is used and rho C is the solid density of the catalyst. So, if we know what is the bulk density, then we can plug it in here, and then we can find this expression, and N is the order of reaction, N stands for the order of reaction, the reaction order, and Kc is the corresponding mass transfer coefficient. Kc is the mass transfer coefficient. So, one needs to estimate what is the mass transport coefficient for transporting the species from bulk to the surface of the catalyst, and then one needs to know what is the concentration of the species in bulk, which is again a measurable quantity, and one may also use different appropriate correlations. There are several correlations which are available to estimate the mass transport coefficient. One may use the appropriate correlation in order to estimate what is the value of this mass transport coefficient for the given conditions, that is for flow through packed beds. So, once we know these numbers, we will be able to estimate what is this quantity on the left hand side, and if this is smaller than 0.15, then the external diffusional limitations are not playing any role and that can be ignored. If it is greater than 0.15, then certainly external diffusional limitations have to be taken into account. So, now if the Mears criterion is satisfied, if the Mears's criterion is satisfied, then this means that there is no concentration gradient between the bulk gas and the external surface of the catalyst pellet. So, there is no concentration gradient between the So, there is no concentration gradient between the bulk gas and the catalyst surface if the Mears's criteria is satisfied. Now, we looked at the concentration gradient. Now, one may ask what is the what about the temperature gradient? So, can we get an estimate, can we find a criteria in order to know whether the temperature gradient, external temperature gradient, does it play a role? That is the gradient of temperature between the temperature at the surface of the catalyst and the temperature of the bulk stream, does it play any role in the in limiting the reaction? So, Mears has come up with another criteria. So, it is Mears's criterion 2. Now, this suggests that if the modulus of this expression, where delta H is the heat of reaction into minus R A prime, which is the observed reaction rate, multiplied by rho b, which is the bulk density of the catalyst, into the radius of the pellet that is used, multiplied by the activation energy E, divided by a corresponding heat transport coefficient. There are several correlations which are available in order to estimate the heat transport coefficient, multiplied by the square of the bulk temperature of the fluid stream, multiplied by the corresponding gas constant. So, if this absolute value of this ratio, if that is less than 0.15, then it means that the temperature gradient does not play any role, which means that the bulk fluid temperature is approximately equal to the catalyst surface temperature. Note that intraparticle gradients need not necessarily be negligible. However, Weisses-Prater criteria can be used to identify when these gradients may be neglected. So, this is an important criterion. So, these two criterion can actually be used, but these two criteria can actually be used in order to decipher whether the particular reaction is being conducted under diffusional limitations or not. So, now let us summarize what we have learned so far. So, we have looked at the Weisses-Prater criterion. Weisses-Prater criterion, and the first one is to decipher whether it is the Weisses-Prater criterion is basically to decipher if the diffusional limitations exist, and then we looked at the Mears's criterion. So, the first criterion is basically to see if the external diffusional limitations exist, to check whether the external diffusional limitations exist, and then the second one is to check whether the temperature gradient is important. External temperature gradient is important. So, these three criteria, Weisses-Prater criterion and the Mears's criterion, they play a very important role in real situations, because if the experimental data is available, then this information can actually be used in order to decipher whether the reaction is being conducted under diffusional limitations or not. So, next let us look at design of a packed bed reactor as to how we can incorporate the concept of effectiveness factor into the packed bed reactor design. Now, let us consider a packed bed reactor. Packed bed reactor is essentially a tube filled with a catalyst, and the fluid stream goes from one end of the tube into the other end of the tube. So, let us consider a tube. Let us consider a tube, and there is a fluid stream which goes into this tube and it leaves the tube from this end. So, if I mark this as z equal to 0, if z is my coordinate system, so 0 to L, so L is the length of the reactor, and if AC is the cross sectional area of the tube, and now I can write a mole balance in order to capture the dynamics or the behavior or the relationship of the conversion with all the other parameters. So, now if I write a shell balance, I now identify a small shell which is filled with catalyst, and let us assume that the volume of this shell is delta V, and the amount of catalyst which is packed inside is delta small w, and if the location where this element starts is z and the location where it ends is z plus delta z. So, this immediately means that delta w, which is the differential amount of catalyst which is present in that location, should be equal to the bulk density of the catalyst multiplied by the cross sectional area multiplied by the delta z, which is the thickness of that particular element that we have chosen. So, now we can write a mole balance for this small element, and we can find out what is the model equation which captures the relationship between the concentration of the species which is undergoing the catalytic reaction with respect to other parameters. So, suppose if the the flux of a species that enters this small element is WAZ, that is the flux that enters at that location, and the flux that leaves is WAZ evaluated at Z plus delta Z. So, that is the flux that leaves that location. Then we can write a mole balance and the mole balance is essentially the rate in the rate at molar rate at which the species enters that element minus the molar rate at which the species leaves the element plus whatever is generated, that should be equal to 0 under steady state conditions. So, if we assume steady state conditions, then this is the balance that captures the process that is happening in this small element. So, what is the rate at which the species is getting into the element? That is given by the cross sectional area AC multiplied by the flux with which the species is actually entering into that element, which is WAZ evaluated at that particular location, minus the rate at which the species leaves is given by the cross sectional area multiplied by the flux at which the species leaves that element, that is WAZ at Z plus delta Z, and the generation is given by the reaction rate per unit weight of the catalyst multiplied by the amount of catalyst which is packed inside that small element delta Z. So, now we know that if the reactor volume is constant, we know that we can actually rewrite this expression as delta W is equal to rho B AC into delta V delta Z, that is the differential amount of catalyst that is packed inside that element, and so we can now incorporate this into the model, and therefore, the model will be AC into WAZ minus AC AZ at Z plus delta Z plus the rate multiplied by the bulk density into the cross sectional area into delta Z equal to 0. So, that is the model. Now, we can divide this whole equation by cross sectional area into delta Z. So, that will be 1 by AC into delta Z, that is multiplied by AC minus Z plus delta Z plus R A prime into rho B into AC into delta Z, that is equal to 0. So, now if we take limit delta Z going to 0, that if the element is very small, infinitesimally small, then the model equation becomes minus d W A Z by d Z plus R A prime into rho B equal to 0. So, this is the mole balance for species A, which is undergoing a heterogeneous reaction in a packed bed reactor, where WAZ is essentially the flux with which the species is actually entering the flux of the species at a particular location Z. Now, if I assume that the total concentration is constant, so if you assume that the total concentration of species, all species is constant. So, total concentration of all species put together, if it remains constant, and if that value let us say is C. Now, the flux with which the species crosses a particular location, that can be written as minus DAB, which is the diffusivity of the species, equimolar counter diffusivity of that species A, multiplied by the concentration gradient DAB divided by dz plus YAB, which is the mole fraction of the species, multiplied by the WAZ, which is the flux of the species at that location, plus the flux of species B at that location. So, now if we stare at this equation, the first term here corresponds to the diffusion term, corresponds to the species diffusion, and the second term corresponds to the bulk flow. second term corresponds to the bulk flow, which is like a convective transport, and the first term corresponds to the diffusive mode of transport. So, now if we know what is the superficial velocity, so suppose if the superficial velocity is u, then the total flux that is crossing a particular location W A z plus W B z, that should be equal to the total concentration C multiplied by superficial velocity u. So, now plugging in this expression, we can rewrite the expression for the flux of species, that is W A z, and that should be equal to minus d A b into d C A b by d z. So, that is the bulk concentration of the species at that particular location, plus u into C into y A b, y A bulk small b. So, now if you look C into y A bulk is nothing but the concentration of the species at that location, and therefore, it will be minus d A b into d C A b by d z plus u into C A b. So, that is the expression for the flux of species that is crossing any particular location z inside the reactor. So, now plugging in the expression for the flux in the mole balance, we can rewrite the mole balance as, so now the mole balance can be rewritten as, dAb, which is the dispersion coefficient of the species, into d square C A b by d z square. So, that is the second differential of the concentration of the species, minus u, which is the superficial velocity, multiplied by d C A bulk by d z, plus R A prime, which is the rate at which the species is being consumed, rate at which the species is being generated, multiplied by the bulk density, that should be equal to 0. So, now this first term here, which is the diffusion into the second derivative of the bulk concentration of the species. So, that is because that is due to diffusion, and or it could be either because of diffusion, the transport of species that is captured by this term could be either because of pure diffusion or because of axial dispersion, because of dispersion in the axial direction. So, therefore, for rest of the design equation, mole balances, we would consider dAb, which is the equimolar counter diffusivity, should be approximately equal to the dA, which is basically the quantity that captures the extent of diffusion or the extent of dispersion, or diffusion and dispersion together. Okay. So, hereafter we will refer to it as dA in this lecture. So, the modified mole balance using this representation is dA into d square CAB by dz square minus u into dCAB by dz plus RA prime into rho b equal to 0. So, now using this expression, now we need the next step we need to do is we need to relate RA to concentration. We need to find out what is this relationship with the concentration of the species. So, if suppose if omega is the overall effectiveness factor, if this is the overall effectiveness factor, so it is the overall effectiveness factor, then the rate of reaction R A prime can actually be given by minus R A prime, can actually be is given by minus R A bulk. So, this is the reaction rate in the catalyst. Now, that should be equal to the reaction rate if all the catalyst surface is now exposed and is present at the concentration of the species on the surface, then that will concentration of species in bulk, then multiplied by the overall effectiveness factor will actually be the actual reaction rate inside the catalyst. So, now if we assume that it is a first order reaction if it is a first order reaction, then minus R A prime is given by the effectiveness factor multiplied by the specific reaction constant into the surface area of the catalyst per gram per unit weight of the catalyst multiplied by the bulk concentration CAB. So, now plugging in this expression into the mole balance, we can find that the mole balance is dA, which is the dispersion coefficient, multiplied by d square CAB by dz square, minus u, which is the superficial velocity, into dCA bulk by dz, minus omega into the bulk density rho b into k prime, which is the specific reaction constant, multiplied by the surface area per gram catalyst into CAB equal to 0. So, now if the flow through bed, so we need to solve this equation in order to find out the relationship between CAB and the how the bulk concentration changes with location inside the reactor. So, now suppose if the flow through the bed is large, significantly large, then one can actually neglect the axial dispersion. One can neglect the axial dispersion, and that is not true always, only when this flow through bed is large, and in fact one can actually quantify what is the situation under which the axial dispersion can be neglected. So, the condition that has to be satisfied in order to assume that the axial dispersion can be neglected is given by minus R A prime into rho b, which is the bulk density, multiplied by the diameter of the particle divided by the superficial velocity. If that is much smaller than this quantity u naught dP by dA, then it is acceptable to neglect the axial dispersion from the mole balance. So, this also suggests that when axial dispersion can be neglected, it also suggests that the u into dCA by dz, which is the term that corresponds to the convective transport, that is significantly larger than the diffusive transport inside the packed bed reactor. So, it suggests that the convective transport is larger than the diffusive transport, and under these conditions one can actually neglect the dispersion inside the reactor, and so the modified mole balance which accounts for these assumptions is dCA by dz, that is equal to minus omega is the effectiveness factor into rho b into k, k is the reaction rate constant, and SA is the area of the catalyst per gram of the catalyst, surface area of the catalyst which is available, divided by the superficial velocity into CAB. So, if suppose at the entry of the reactor Z equal to 0, if CAB is equal to the some constant value Ca naught, which is the concentration with which the species enters the reactor, then we can integrate this expression and find that CAB is equal to CAB naught into exponential of minus omega rho b SA by superficial velocity u into z, and or we can use this expression in order to find out what is the conversion of the species in the reactor, and the conversion is given by this expression here, where x is equal to 1 minus CAB by CAB naught, which is equal to 1 minus exponential of minus omega into rho b into k into SA by u, which is the superficial velocity, into z. So, this expression captures the relationship between the conversion as a function of the location inside the reactor, and so this is very useful in terms of estimating what is the reaction, what is the conversion given the overall effectiveness factor and the system parameters and the configuration of the reactor, that is what is the particle diameter, etc. So, what we have seen in today's lecture is we have looked at the criterion for when the internal diffusion is important and when the external diffusional limitations are important, and that is simply based on the experimental data that has been obtained from the real reactor system. And also we had attempted to see how to incorporate the effectiveness factor into the mole balance of the packed bed reactor in order to find out what is how the conversion changes as a function of position in the packed bed reactor. Thank you.